Hello and welcome to the 18th session of the Introductory Biostatistics Distance Learning course. Today, in the 18th session, we're going to talk about estimates of effect, and then we're going to look at the chi-square test and the Fisher's exact test, which we talked about in the last lecture, but illustrate how to carry those tests out using Stata. Okay, so you'll remember that we were talking about cases where we had a binary outcome as well as a binary covariate, and the example we were using was the outcome was disease progression, yes, no, and the binary covariate was whether people had this certain SNP, yes, no. And so first we did a test of proportions, and we were able to get a difference in proportions, and that was our estimate of the effect. Then we said we could carry out the same test using chi-square or Fisher's exact test methods, but there we just got a p-value. We didn't get an estimate of effect. So today we're going to talk about what estimates of effect we can use when we can report when we use a chi-square test, or if we have a small sample size, or if we just prefer exact tests when we carry out a Fisher's exact test. Okay, so let's get started. So first we're going to talk about a quick review of conditional probability. You'll remember we talked about probability being the chance of an event, and the example we used was the probability, for example, that someone has blue eyes. And then we said there's this other thing called conditional probability, which is the chance of an event given a specific event has already occurred. And so one example of that is the probability of blue eyes given, and the way we write that is with this line here, so the probability of blue eyes given that you have blonde hair. Okay? So conditional probability focuses on a specific subset of people or events. So the probability of blue eyes here is pretty low, but if I tell you the probability of blue eyes given blonde hair, that probability is much larger, right? Okay. So which one of these is true? The probability, I'm just going to write it in shorthand. Blue eyes, so BE, given blonde hair, plus the probability of not blue eyes given blonde hair equals 1, or the probability of blue eyes given blonde hair plus the probability of blue eyes given not blonde hair. So which one of these actually adds up to 1? So the answer to this question, hopefully you're guessing as we go along, the answer to this question is this first one. This one adds up to 1, okay? Whereas this one does not, big X. And the reason is, here we've conditioned on the same thing, right? We're conditioning on blonde hair, blonde hair. So given that someone has blonde hair, they either have blue eyes or they don't have blue eyes. And that covers all possibilities for people with blonde hair. That's why we say this adds up to 1. In this case, in the second case, we are conditioning on two different things. Blonde hair in the first example and not blonde hair in the second. So these things don't necessarily need to add up to 1. But this one does. The first one does. Whoops, sorry about that. The first one does need to add up to 1 because we've conditioned on the same thing, which is having blonde hair. Okay? And you'll remember this picture that we used to illustrate this idea was like this. This Venn diagram is what this is called. So here's the universe of people with blue eyes, the universe of people with blonde hair, and somewhere in the middle, these people have both. So those are the people that would be relevant in our conditional probability. Okay? And then out here in this white space would be people who have neither blue eyes nor blonde hair. Okay. All right, with that review in place, let's talk a bit about study designs. So one important study design is called a cohort study. And so what happens in a cohort study is that patients are identified based on their exposure. So sometimes we're interested in a specific exposure, and then we identify people who are exposed to this thing and people who are not exposed. Then we follow them over time to determine if they develop the outcome. Okay? So maybe I should write some of that out. Patients identified based on exposure. And then followed over time. So sometimes when there's a study design like this, people call it a cohort study, or when you follow patients over time, sometimes people call this a prospective study. And that's to be contrasted with a retrospective study. Okay? So a retrospective study is when all the events have already happened, and for example, you go into people's medical records and you see who developed the outcome of interest and whether they had the exposure of interest and so on. So you're looking back in time. That's called retrospective. In this sort of study, which I've laid out here, this would be called prospective, because you're first identifying patients based on exposure, and then you're following them over time in the future. That's called a prospective study. Okay? And then what we do in a cohort study is we compare the proportion of subjects who develop the disease in each exposure group, the exposed and the unexposed. Okay? And then we estimate the probability of disease given the exposure. So you can see why we reviewed conditional probability, because here is a conditional probability. The probability that you develop disease given that you've been exposed to whatever the exposure of interest is. Okay, so this is called a cohort study. Okay. So what's another type of study design? There's this thing called a case control study. Okay, so this is different because patients are identified. Remember, in a cohort study, we identified patients based on their exposure. Here, in a case control study, patients are identified based on the outcome. Okay? So the outcome has already taken place. And we identify patients based on their outcome. Okay? And then patients' prior exposure is determined. Okay? So you can see this is all taking place, this is all kind of retrospective. We're looking in the past. First, we identify patients based on their outcome, which means it's already happened. And then we look at their prior exposure to see if they were exposed or unexposed. Okay? And this is used very frequently with rare diseases. Okay? And you can probably have a good sense of why we use this type of study design for rare diseases, because if a disease is rare, it'll be very difficult for us to find people who have the disease in a cohort study. But instead, if we do a case control, we can look back and see who developed the outcome and then proceed in that fashion. Okay? And again, we would compare the proportion of patients with the prior exposure in the two groups. Okay? So what we're estimating here is the probability of exposure given disease. And again, this is another conditional probability, and you can see it's the exact opposite of what we were estimating in a cohort study. Okay? In the cohort study, again, we were estimating the probability of disease given the exposure. Okay? So it's always important to remember what kind of study design you're working with, because that'll help determine what it is that you can estimate. Okay? All right. So with those two types of study designs in place, let's talk about different measures of association. Okay, so let me pull up one here. Okay, this is the risk difference. Okay, so if I'm looking at the probability of disease among the exposed, and then I'm subtracting the probability of the disease in the unexposed, that gives me the risk difference. Okay? So do these, if I were to add these, here I've subtracted them. If I were to add these, would they sum to 1? No, right? Because I'm conditioning on different things. Here I've conditioned on being exposed, and here I've conditioned on not being exposed. Okay? And so under the null, the risk difference is 0, right? So the null hypothesis is that RD, the risk difference, is equal to 0. Okay? Then there's this other measure, so that's the risk difference. Then there's this other measure here called the relative risk, or also called the risk ratio. It's called the ratio because we're taking one number divided by the other, right? And that's the probability of the disease in the exposed divided by the probability of disease in the unexposed. Okay? So, under the null hypothesis, what is the relative risk or the risk ratio equal to? Hopefully you didn't say 0 like we had here. We said 0 here because we're subtracting, right? If two things are the same and we subtract them, then we get 0. However, if two things are the same and we divide them, we get 1. So that's an important distinction to keep in mind. Okay? So the null value for the relative risk or risk ratio is 1 because we're taking two numbers and dividing them. So if I take 5, let's just make a silly example. If I take 5 minus 5 up here, it's equal to 0. But down here, if I take 5 divided by 5, it's equal to 1. And that's why the null values differ for these two measures of association. Okay. So let's take a look at a table of what this might look like. Here. Okay, so we have the exposed here, the unexposed here, the people who got the disease here, and the people who didn't get the disease here. Okay? And then we have these cells A, B, C, and D, and then the margins as well. Okay? So here, in this case, the probability of disease positive given that you were exposed, so exposure positive, which cell would that correspond to? Okay? So we've conditioned on exposure positive, right? So that means we're here in this column. Okay? So that means our total is M1. Okay? And the people among those who have the disease are these A's, right? So it'd be A divided by M1. Okay? And so similarly, the probability of being disease positive, given that you're unexposed, so that exposure negative is equal to B over M2. Okay? And so if we took the difference of these two, if we took A over M1 minus B over M2, that would give us the risk difference. That was that first measure of association that we talked about on the previous slide. Okay? All right. So that would give us our point estimate, and hopefully you're getting comfortable with these concepts now. Now that we have a point estimate, we just subtracted them. The next thing we need is a confidence interval for the risk difference. Okay? So there are several different types of confidence intervals available for the risk difference. That's what statisticians work on, spend their time trying to figure out how to calculate these things. But luckily we can just take that as given. So statisticians have said, hey, if you take the difference in these two proportions, one minus the other, it turns out it's normally distributed, and here's the mean of the difference, and here's the variance of the difference. Okay? So given that very important result, that the difference in these two proportions is normally distributed, we can then develop a confidence interval, which is what we're interested in. And that would look like this. Okay? So we take our estimate, P1 hat minus P2 hat, minus critical value, Z alpha over 2, times the estimate of the standard error. That's why we add the square root. Remember here, this was the variance. And so in order to get the standard error, we take the square root, and then comma, the point estimate again, but now plus critical value times standard error. So hopefully the form of that is very familiar to you by this point. It's the same form we've always used for developing our confidence intervals. Okay, so that's the confidence interval for the risk difference. What about the relative risk or risk ratio? Let me pull up the table that we were working with again. Here it is. So the risk ratio, I won't go through the derivation that we did the last time. The risk ratio, now instead of subtracting the two numbers, we divide them, right? So we had A over M1 divided by B over M2. Okay, so that would be our estimate of the risk ratio. So again, we have our estimate here. So the next thing we need is a confidence interval. Okay. So to construct a confidence interval, we again use a normal approximation. But in this case, the confidence interval is based on a log transformation of the risk ratio. Okay. So people often use this notation interchangeably. So you might say the log transformation of the risk ratio. That's the same thing as the natural log. People often use the same notation for these things. Okay. So if I write log, I mean natural log. Which is what it is here, okay? And hopefully you remember the natural log from your high school math classes. But just as a quick review, if we take the exponentiate the natural log of the risk ratio, we just get the risk ratio back, okay? So exponentiation and the log are kind of inverse transformations, okay? So if we do both of them, we end up with the risk ratio again. Okay? Okay. And so you might still be wondering, why are we working with the natural log of the risk ratio? Well, it turns out it's generally easier to deal with subtraction rather than division. And the natural log has this other property whereby the natural log of the risk ratio, which is to say the natural log of one probability divided by another probability, when you divide things in a natural log, it's the same as subtracting. So that's equal to the log of P1 minus the log of P2. Okay? And as another just example, the same is true for, so if I had the log of A times B, a property of logs is that's the same as the log of A plus the log of B. Okay? So that's one of the reasons that we work with the log of the risk ratio, because it's easier to deal mathematically with subtraction rather than division. Okay? So with that being said, we can estimate the standard error for the log of the risk ratio using a formula that I'm going to pull up now. Okay, here. Okay? And you'll remember these numbers are the numbers, the A's and B's and C's and D's and M1s and M2s are from those tables that we were looking at. Okay? So again, don't worry about the specifics of the formula. Stata is going to take care of all that for us, but it's good to know how these confidence intervals are being constructed. Okay, so now we have an estimate of the variance or the standard error. We can create a confidence interval using the same format that we've used all along. So let me pull that up. Okay, so we take our estimate, natural log of the risk ratio, minus critical value times standard error, comma, our estimate, plus the critical value times the standard error. Okay? Same format we've used all along. So that gives us a confidence interval for the natural log of the risk ratio, but obviously we want a confidence interval for the risk ratio itself, not the natural log. So what can we do to back transform? Hopefully you're thinking, well, we can exponentiate, right? Because we said taking a log and exponentiating are inverse functions. So I just took everything I had here previously, and I took e to that stuff. Same with the other confidence bound. And then I can end up with a confidence interval for the risk ratio. Okay? All right, good. So again, big picture is we're looking at measures of association for these different types of studies, and we can look at the risk difference or the risk ratio, and then we can construct confidence intervals for both. So what does this look like in Stata? Here it is. So you can see Stata very helpfully gives us the risk difference here, as well as the risk ratio here, okay? As well as the 95% confidence intervals for both, okay? As well as, here's the risk in the exposed, 0.16, looks like 16.2% of them, of the exposed, develop the disease, while 11.2% of the unexposed develop the disease. And that's why the risk difference, if I take 16.2% minus 11.2%, gives me this 5% for the risk difference. Okay? Alright, so now I can tell whether this difference is significant just by looking at the confidence intervals, right? So if I look at the confidence interval for the risk difference, remember, what's the null value for the risk difference where we subtract numbers? The null value is 0, right? And since 0 is contained in this confidence interval, since this side is negative and this side is positive, so somewhere in the middle here is 0, we know that the difference is not going to be significant, okay? And we also said for the risk ratio, where we divide two numbers, sorry it's getting messy, the null value here is 1. And it looks like 1 is in the middle of that confidence interval, so as they should, they do agree. And we can confirm that with our p-value down here from the chi-square test. Okay? So it doesn't look like there's any significant difference. Again, this is that example we've been working with about disease progression, yes, no, based on SNP, yes, no. Okay. So how do we interpret these things? Well, the estimated risk difference, we said over here, was 0.05. So the interpretation is that the risk of progression for patients with this particular SNP is 5% higher than for patients without the SNP. Okay? And that the 95% confidence interval goes from negative 0.05 to 0.15. And so since that contains 0, we say there is no significant difference between the SNP groups. Okay? So now how about the interpretation for the relative risk or risk ratio? Well, the point estimate here is 1.45, if I just round that second number, 1.45. So the interpretation of this is that the risk of progression for patients with the SNP is 1.45 times higher than for patients without it. Okay? So now we're talking about it's 1.45 times higher, okay? That's because we've taken the ratio, which is why our interpretation is a little bit different. Remember, for the risk difference, we said that it was 5% higher, absolutely, just because we'd subtracted the numbers. Now we say that it's 1.45 times higher because we've taken the ratio. Okay, and the corresponding 95% confidence interval goes from 0.7, if I round up, 0.698 becomes 0.7, all the way up to 3, if I round 2.997 up to 3. And so 0.70 to 3.0. And since 1 is right in the middle of this, we can again say that there's no significant difference between the groups. Okay? All right. So let's bring this whole, what we've talked about so far, full circle. So we've talked about the risk difference and the risk ratio, and we also talked about cohort studies versus case control studies. So can we estimate these quantities of interest with any study design? Well, the answer is not directly. Okay. So in a cohort study, the probabilities of interest, which are the probability that you have disease positive given exposure positive, can be estimated. In a case control study, the probabilities cannot be estimated directly, so we have to do a little bit more work. Okay? Remember, we said that in a case control, we're able to, this is what we're after, right? We want to know if you have the exposure, what's your probability of disease? But we said in a case control we can estimate the probability of exposure positive given disease positive. And the reason for that is because in a case control study, we're not looking at everyone, right? We're just looking back in time to see who developed the disease and who didn't. So we're identifying cases and controls and then looking also backwards at their exposure. So that's why there's this difference in what we can estimate. Okay, so what can we do to solve this problem? That's where this thing called the odds ratio comes into play. This is something that we see in the medical literature very frequently. And so we're going to get at a reason why the odds is so frequently seen. So the odds is defined, you may have heard of the odds in situations where people are gambling. They'll say the odds of this team winning or that team winning are such and such. Excuse me, so the odds is defined as the probability of an event, P, divided by the probability of it not occurring, 1 minus P. Okay, so that's the odds. Now, to get an odds ratio, you might be able to guess, we just take 1 odds, P1 over 1 minus P1, and divide by another odds, P2 over 1 minus P2. So hopefully you can see why this is called an odds ratio, right? Here's an odds, here's an odds, and I've taken the ratio of them, so that's called an odds ratio. So let's contextualize this in terms of our example, and that would look like this. So the odds ratio is the odds in the people who are exposed divided by the odds in the people who are not exposed. Okay? So the odds in the exposed, the numerator, is the probability of disease positive given exposure positive divided by 1 minus that quantity. And then the odds of in the unexposed is the probability of disease positive in the unexposed divided by 1 minus that same quantity. Okay? So under the null, what is the odds ratio? Well, this is a ratio again, right? Just like the relative risk or that we were looking at before, or risk ratio. And we know that the null value when you divide two numbers is 1. Okay? So that is the null value of the odds ratio. Okay. So let me bring up this table again that we've been using to summarize our data. Okay, and then now we can think about what we can estimate. Okay, so here in this first line we're saying what is the probability of disease positive given exposure positive. So exposure positive is this column, right? So that's why the denominator is A plus C, because it's these guys plus these guys. Instead of A plus C, we could have also written M1, right? And then among those, the people who have the disease, yes, are the people with A. So that's why we have A divided by A plus C. Okay? And then the odds of disease given, whoops, sorry about that. The odds of disease given that you're exposed can be written out as such. And then we can simplify it, right? If we carry out this calculation, we can see we're dividing by A plus C in the numerator and the denominator, so those cancel, and we end up with A divided by C. Similarly, the odds of disease among the unexposed can be reduced to B over D, and then we take the ratio of these two things, A over C divided by B over D, and that can be simplified to AD divided by BC. So that's our estimate of the odds ratio. Okay? So this is the estimate of the odds ratio from a cohort study. Okay? The odds ratio from a cohort study. So hopefully this is all starting to come together for you now. We talked about the measures of association that we're interested in. We talked about different study designs, and then we said, wait a second, we can't exactly get at the measure of association we want to with all study designs, namely with a case control study. So instead we introduced this new measure called the odds ratio, and we said, hey, let's take a look at what the odds ratio looks like for two different types of study designs. So here's the odds ratio for a cohort study, which is AD over BC. Okay? So now, if I move to a case control study, this same table, right? And then I pull up the corresponding measures here. Sorry, it looks like I'm going to run out of room. Try to fit these as best I can. Okay, so you remember now we're dealing with a case control study. And how do I know I'm doing that? Because look, I'm estimating the probability of exposure given disease. Remember, in a cohort study, these were flipped. So I know that I'm in a case control setting because this is what I'm estimating. So the probability of exposure given disease, so first we look at everyone who has disease, that is this column here. So it's A plus B. That's why this is here in the denominator. And then the people who are exposed among those are the A's. Okay, then we get the odds again. We go through the same calculation we did before. The odds of exposure given disease is A over B. Then the odds of exposure given no disease is C over D. Now I have two odds, odds 1, odds 2. Then I can take their ratio, the odds ratio becomes AD over CD, and then it's AD over BC, which is our measure of the odds ratio. So this is amazing, right? We're in a case control study, and it turns out that the estimated odds ratio from each type of study, the case control and the cohort, ends up being the same thing. Okay? So therefore, we can complete a case control study and get an estimate that we really care about, which is the effect of the exposure on disease. Okay? So this relationship, this kind of very useful property of the odds ratio, is why we see it so much in the medical literature. Or at least part of the reason why. Another reason why we see the odds ratio so much is because it's what comes out of logistic regression analyses, which we'll talk about in a future lecture. Okay, so a very cool result. Even if we have these two different types of study designs, if we use the odds ratio, they end up being equivalent in both study designs. Excuse me. So now we have our estimate, the odds ratio. So hopefully you can very simply guess the next step. Well, we need a confidence interval. Okay. So what does that look like? We're not going to go through the derivation, but here's our progression, no progression of disease based on whether you have the SNP or not. Okay, so based on this table, the estimated odds ratio is going to be 12 times 103, remember, AD over BC, divided by 13 times 62, and it turns out that this is 1.53. That's our estimate of the odds ratio. Then Stata, we're not going to go through the derivation. Stata can give us a 95% confidence interval, which in this case it turns out goes from 0.66 to 3.57. And so would you reject or fail to reject the null hypothesis? Remember, the null hypothesis for the odds ratio is that it's equal to 1. Turns out 1 is right in the middle of this, so we would fail to reject, right? Because our confidence interval contains the null value, we would fail to reject and conclude that based on our sample, there's no significant difference, okay? All right, so how do we interpret this odds ratio? Odds ratios, they have this very nice property, which we talked about, that they can be derived from these different study designs, and they come out of logistic regression analyses. But the downside of them is that the interpretation is a little bit more difficult. Okay, so the interpretation of this, our estimate of 1.53, would be as follows. Okay, that the odds of progression for patients with the SNP is 1.53 times higher than the odds for patients without the SNP. Okay, so let me say that one more time. The odds of progression for patients with the SNP is 1.53 times higher than the odds for patients without the SNP. Okay? So that's kind of a difficult interpretation because it's all in terms of odds. And unless you're very quantitative, we don't really intuitively think in terms of odds. Okay? So the interpretation is a bit difficult, but it comes at the benefit of all these other nice properties that we have for the odds ratio. Okay? Alright, so what would this look like in Stata? Here it is. Here I've put in the numbers for my table. This OR tells it to look at the odds ratio, and this wolf is what gives me the confidence interval. Okay, so if I go down here, here's the odds ratio. Here's my 1.53. Here's the corresponding 95% confidence interval. Some statistician named Wolf was responsible for deriving this, so that's why his or her name is there. I'm not sure if it's a man or a woman. So, but that's the reason that is there. Okay. Okay. So again, that's based on the normal approximation. We can also, just like we had Fisher's exact test, we can also have one here where if we put in the same numbers, but we don't put in Wolf, you can see we get our odds ratio. The estimate doesn't change, 1.53, but the confidence interval is now an exact confidence interval, and it's slightly different from the one based on the normal approximation above. Okay. Okay, so that's what it looks like in Stata. So let's talk about the odds ratio versus the relative risk or risk ratio. Okay? So the relative risk is much more intuitive. It's much easier for us to understand. If we get a relative risk of 2, we can think, oh, this thing is twice as likely in the one group compared to the other. But on the other hand, if we get an odds ratio of 2, that tells us the odds of an event is twice the odds of the other. That's very hard to think about. So the relative risk is much more intuitive. So people often talk about the situation if we have a rare disease, something that occurs very, very infrequently, which is often the case for a case control study. Remember, we undertake a case control study if we have a rare disease because we know that people with the disease are going to be hard to find. So if we undertake a case control study, we can look in the past to see whether they had it or not. So if we're working with a rare disease, we'll have this property, that the probability of not having the disease among the exposed is very similar to the probability of not having the disease in the unexposed, which is close to 1, right? We're saying it's close to 1 because it's a rare disease. So I should write that down. If it's a rare disease, then, then the following holds, okay? If something happens very infrequently, we expect the people without disease to be the huge majority, which is why this holds, okay? So therefore, in these cases, again, only in cases where the disease is rare, then if we go through this calculation, here's the odds ratio, here's the definition of it, and then based on this property which we showed here, that's very close to, that's why we have these squiggly equal signs. That means it's kind of a close approximation to the risk ratio. Okay? So therefore, in these cases, the odds ratio can also be considered a close approximation of the relative risk for rare diseases. Okay? All right. So we could go through our 7 steps of hypothesis testing, just like we've done before, writing out the null and alternative hypotheses, talking about the type of data we have. Here we have a binary outcome and a binary predictor. Then we can look at the risk difference, which is our what we're going for, and then our test statistic is the estimated odds ratio. Then we look at our p-value, and then our p-value in this case was greater than 0.05, so we failed to reject. And then we concluded that based on our sample, there's no significant association between SNP and disease progression. Okay? So what are our conclusions here? So based on study design, we can estimate certain measures of effect, but the odds ratio can be estimated from a case control study or a cohort study. Okay, and this property, as well as logistic regression, are why we see the odds ratio so frequently in the medical literature. And so confidence intervals for each of these can be calculated and are available using Stata. Okay? Alright, so let's move on to Stata and think about how we can do these things that we've talked about using the statistical software program. Okay, so here I am in Stata. Again, I'm working with the SEPO dataset. You'll remember in the previous lecture we talked about the chi-square test. So we want to talk about how we can carry out the chi-square test in Stata. Okay, so again, our null hypothesis is the same, that the probability of disease progression among those with the SNP is equal to the probability of disease progression in those without the SNP. Okay, so how can we do this? Sorry about that. We're working with the SEPO dataset, and we're trying to assess whether the probability of death is impacted by gender. Sorry about the confusion there. So the disease progression SNP example was our lecture example. Our Stata example that we're carrying out is the SEPO, whether people died on the study and whether that's impacted by their gender or sex. Okay? All right. So if I want to carry out a chi-square test, I simply go down here into the command window and I can write tabulate, and then I write my my binary covariate, which in this case is sex, and then my outcome variable, which is death, C-E-N-S, death sensor, and then comma, space chi, C-H-I, 2 for chi-square. Okay? So you'll see it provides this really nice table to summarize the data. Here are the number of men who didn't die on the study, 187. The number of men who did die on the study was 12. The number of women who didn't die on the study was 426. And the number of women who did die on the study was 25. Okay? And so we want to know, does gender impact whether patients died on the study or not? And so here's our corresponding p-value, 0.805. It's a very large p-value. So we would fail to reject and conclude that based on our sample, gender did not have a significant impact on whether patients died on the study or not. Okay? So again, you remember that the chi-square test relies on this normal approximation. We had this rule of thumb that each of the numbers here in these four numbers should be greater than 5. So we can also do a Fisher's exact test if that doesn't hold, or if we just want to be more conservative. Okay, so we type in the same beginning as we did before. Tabulate sex, death, C-E-N-S, comma. Now instead of writing chi-square, C-H-I-2, I write exact. Okay, and you'll see the numbers are the same, but here's my p-value for the Fisher's exact test, 0.855. And so we reach the same conclusion as we did before, namely that we fail to reject the null hypothesis and conclude that based on our sample, there's no significant effect of gender on whether patients died on the study or not. Okay. Now, if we didn't know these commands, which we obviously wouldn't our first time around, we can carry this out using the drop-down menus. So I'm just going to go to Statistics, and then Summaries, Tables, and Tests, and then Tables, and then, Summaries, Tables, and Tests, Tables, and then two-way tables with measures of association. Okay, so Statistics, Summaries, Tables, and Tests, Tables, and then two-way tables with measures of association. Okay, you can see I've already entered the things here. So for the row variable, I chose sex from the drop-down menu. If you just go along, you can find sex there. And then for the column variable, I put in death sensor, death, C-E-N-S. And then here, you can see in the test statistics window, I can choose the Pearson's chi-squared and the Fisher's exact test. Okay? So I can conduct both of these tests simultaneously, which is nice. Then I'll hit OK. You can see Stata gives me the corresponding command. It's just like what we were doing before, but where we wrote comma, chi-square, or exact, this writes comma, chi-square, and exact. Okay? So we get both p-values down here. Here's the p-value for the Pearson's chi-square, 0.805, and here's the p-value for Fisher's exact test, 0.855. Okay, good. So we were able to carry out both tests simultaneously using Stata. Okay. So you'll see, again, hopefully this is all coming together nicely. When we carried out the Fisher's exact test or Pearson's chi-square, all we got was a p-value. We didn't get a measure of the effect, right? So that's why we had this discussion of the odds ratio earlier in this lecture. So how can we get the odds ratio for this setup? Okay. So it turns out that in order to be able to get the odds ratio, Stata requires the data to be in a certain format. Okay. So that's why I'm going to create. It requires the data to be zeros and ones. Okay. So if I do a tabulate on death censoring, you can see it's already zeros and ones, so that fits our required format very nicely. But if I tabulate sex, it's male and female, and it turns out it's encoded in this data set as ones and twos, and Stata requires it to be zeros and ones. It's kind of an annoying formatting requirement. Okay, so in order for me to get the sex variable in the format that it requires, I'm going to generate. Remember, we talked about how to make new variables. I'm going to type in generate, and I'll call it sex2 equals, and you'll remember I said sex is, right now it's encoded as ones and twos, so to get it at zeros and ones, I'm just going to take sex minus 1. That means the twos are going to become ones, and the ones are going to become zeros. Okay? So now if I tabulate this new variable I created called sex2, there it is, it's zeros and ones. Okay? Alright. So, how do we get our estimate of the odds ratio now? So remember, we talked about two study designs. One was a case control and one was a cohort. Here, obviously, we don't have a case control. This is a cohort study. This was a prospective cohort study about HIV disease. So in order to get the odds ratio, we're going to go to the following drop-down commands. I'll go to statistics, and then we go further down to epidemiology and related. So statistics, epidemiology, and related, and then tables for epidemiologists. And you'll see here that there's a cohort study risk ratio, and there's a case control odds ratio here. Okay? There's also matched case controls and things like that. So different study designs can be accommodated. So you always want to think, what sort of study design am I dealing with? And that should guide the type of analysis that you do. So here we're in a cohort study, so I'm going to choose cohort study risk ratio, etc. Okay, and you can see for the case variable, that determines, I've put in death censoring, so that's death, yes, no. The exposure variable, I've put in sex. Then if I go to options, you'll see these four things across the top. I'll choose options. I want to click on this thing that says report odds ratio. Okay? And you can see there's the Wolf approximation, there's the Fisher's exact, so I'll just choose all of them, and I'll hit OK. Whoops, sorry about that. So the mistake I made was I used the sex variable, which wasn't in the proper format, when I was supposed to use the sex2 variable, which I created for this exact purpose. So I'll go again, statistics, epidemiology and related, tables for epidemiologists, cohort study risk ratio, and instead of sex, I'm going to drop down this menu and choose sex2, and I'll hit OK. Alright, there it is. So you can see my cases and non-cases. The cases are the people who died on the study, the non-cases didn't die. Exposure and unexposure is a different way of just saying male and female. And then you can see here, here's my point estimate of the odds ratio, and then my corresponding 95% confidence interval, which goes from 0.44 to 1.85. And so you'll see that 0.44 to 1.85, obviously the value of 1 is in that confidence interval, and so we would fail to reject, which is consistent with our two-sided Fisher's exact p-value. Okay? All right. So that's kind of a nice way to bring this all together. We talked about different study designs, how different study designs enable us to estimate different things, but that one really nice feature is that for both the case control and the cohort study, we can estimate the odds ratio, and then we looked at how to do the chi-square test, Fisher's exact test, and get odds ratios in Stata. Okay, so I will stop there. We covered a lot, and I will see you in the next session.